I'm gonna start in a second here. Just one second. All right, so today we are going to be looking at ESM2, which is the protein folding model that Meta or Facebook released, where we looked at the paper yesterday, and today we're going to kind of dive deeper on the actual code base, see if we can run some of these models and maybe look at what's going on here. So there's a couple different models. There's basically ESM2, which is kind of the encoder, if you want to think of it that way, right? It converts a sequence into a feature vector that can then be used to predict structure and other properties, so you can kind of create your own head. In the paper, they use this ESM-fold head, which actually goes ahead and predicts the 3D structure of the protein. So first thing we're going to do here is we're going to create a new Python virtual environment, and then we're going to activate that. And what this will allow us to do is it will allow us to kind of keep our Python dependencies separate between this project and other future projects. So then we're going to let's go into our dev folder, and let's go ahead and clone this repo here. We're going to copy that, and we're going to clone it in here. So that'll go ahead and create the ESM directory. We can look at what's in here. It should basically match the GitHub dataset. So I think first thing we need to do here is Getting started with this repo. You can use this one-liner for installation. Okay. So they do have a latest release or the bleeding edge. So let's actually see when we'll go into the here and we'll do pip fair ESM is the name of the repo. So let's go pip fair ESM. So we can go onto the PyPy page and figure out when the latest release is. So the latest release is October 31st. That seems, if we look at the Hugging Face for this, a lot of the models have been uploaded by this guy here, Rocket Knight. And it looks like a lot of them were uploaded 5 days ago. So maybe let's go ahead and use the latest version of this repo. So you can either pip install directly from this ESM GitHub, or you could have run the setup.py. Pip install -- upgrade pip, because apparently our pip isn't upgraded, and somehow this is not working. Cannot determine archive format. So why don't we instead which Python version 3.8, okay. Python, or no, pip install -e dot. Okay. So this installed the fair ESM. Okay, so now we're going in here. Let's make this a little bit bigger. But we see that if we actually want to use the ESM fold model, it's on a separate kind of sub package within the, so if we go to project description, there's maybe a different one here. It's fair ESM, and then ESM fold. Is that ESM fold all one word? Fair ESM fold. Okay. Can't get the fair ESM fold. Okay, so now this is downloading a couple different things. It's downloading PyTorch, Ninja, BioPython, DeepSpeed. One thing that we keep running into when we go into these things is we'll download the wrong version of PyTorch for the specific version of CUDA that we have. So just for context here, we do have, let's do every 0.1 seconds. This is our graphics card. It's a 1080, so it's kind of an older graphics card, but it's running CUDA 11.6. You can see it up here. Okay, it looks like we got the right installations though, so let's go back here. Fair ESM, cool. Okay, Control W, get to the back to here to the pip starter. So OpenFold requires NVCC, so okay. If OpenFold installation fails, blah, blah, blah. We provide the ESM fold conda environment. Okay, so there's a conda environment if we wanted to do that. We also support PyTorch Hub. Okay, so they have some stuff here. Why don't we go ahead and actually, let's go to our dev folder inside our public better. There's a folder in there that I made called bio. Let's go ahead and touch a ESM test.py. Then let's go ahead and open a VS Code in here. Let's make this a little bit bigger. Close this, open up ESM test, and let's go ahead and import torch, import ESM. So first thing we're going to do is we're going to save that and make sure that that even runs. So Python ESM test. All right, we're good. So it does run. So you see here how it highlights not accessible. So that's basically because this we need to point VS Code to the right Python environment, so we're going to give it this ESM Python environment. It still doesn't like so it does look like the ESM dependency is not getting found in VS Code, but it is there. Resolved report quick fix. No, it just wants me to unuse it. Okay. So first thing we're going to do is we're going to load the model here. Model alphabet. And if you actually look at this, GitHub Copilot is suggesting the first version of ESM, but we want the ESM2 T33 650 mil UR50D. So the 650 might be a little bit too big, so let's this is the 650 mil parameter. Let's go ahead and get one of the smallest one. I think they have an 8 mil parameters one. So if we go here, go back up to the list here. Specialized for predictor of variant effects. So this is actually the one that is getting downloaded here. Inverse folding model. Okay, so it's one of these. Okay, so they have a link here with better pre-trained models. Here we go. This is the one that they want us to use here. UR50S, UR50D, T34. Here, this is the one we want. We want this little tiny boy right here. So let's do model alphabet equals sem.pretrained.esm1. No, actually, this is the one we want. Yeah. We don't want ESM1, we want ESM2. So if we save that, let's actually look at our GPU when we run this. Okay, it's downloading these models, putting them inside the Torch model cache. So right here. So we can actually see what that is. So it's going to take a second to download, but you can open up a new terminal here. Do ls-lht, put that in there. It's still going. This is not even going to load. We're just going to Control-C out of that. Go back to VS Code. Let's go ahead and comment that out. That's going to be way too big. It was already 1.7 gigs. So let's go back here. Let's rerun this. It'll download the small model. And there we go. This small model here is 29 megabytes, so that's a lot more manageable. Cool, so let's go back to VS Code here. And let's go to our quick start. Okay, so we're here. We loaded the model in the alphabet. We now also need the batch converter. This is 29 megabytes. It's over 1 gig. Okay. So batch converter. Get rid of the caps lock here. What exactly does this do? If only we had this ESM. Then we could figure out what's actually going on behind there, but VS Code doesn't want it. And then we go model.eval, and this will put it in evaluation mode, disable some of the training stuff such as normalizations and dropout and things like that. And actually we can try CUDA, so let's actually see if we can see this bump. So right now we're at 1,300 megabytes out of 8,100. So out of 8 gigs, we have about 1 filled. And that's because we have 2 screens running. So if we were to turn off some of our monitors, you would see that go down. But let's go ahead and run this, and you'll see the model. It'll get loaded, and you can see it on the NVIDIA. So there we go. So the model was loaded, and we saw that spike up there for a second. So we can actually do it again. You see it? You see it went up to like 1,800. So that's the model itself. Let's go back to here. Okay. So we prepare our data First two sequences from ESM split dataset superfamily. Okay. I really want to be able to see what this batch converter is, so why don't we exit out of VS Code here and see if we can, when we reopen it, maybe we can get it to reload the dependencies. Let's see if we can actually solve that. Pylance missing imports VS Code. You have to add the paths from which you import what is needed. All right, so what we'd have to do here is pym activate ESM protein, clear. Let's do Python import ESM file that'll tell us the location. And let's put this in the Python path. To Python path. Okay, so we're going to export Python path, and we are going to go ahead and Python path. Okay. So we're going to go ahead and put our dev folder inside that Python path. So hopefully it should find the ESM library that way. So we went ahead, added that in there. Let's restart VS Code again. And I think we're getting it. No, we're still not getting it. Inside .vs Code, you will have a settings.json. Okay, is there a settings.json in here? Vim.vs Code argv.json. Extensions, maybe there's a setting.json in there. No. Let's do a settings.json, and then inside this settings, let's do a open bracket, close bracket, and then in here we'll do copy that. Python analysis extra paths, and we'll go ahead and say home trend -dev -esm. And then do we need a comma at the end of this? Nope. Okay, let's close out of this again. Run it again. Now do we have it? Go to definition, no definition. Damn. Alright guys, I don't know what's going on here. Something more with our VS Code, but we're just going to go back to what we were doing here. Maybe we can look inside the repo itself. So maybe we can open up a VS Code for the repo itself so we can explore it there. So let's go into dev ESM, and then we'll open up a VS Code there as well. And go ahead, put it here. Close out of this. All right, what do we got? Inside ESM. Oh, they have a little examples. Okay. Infer, fair scale, readme. MSA pre-training. Okay, I mean, we don't really care. What we're actually interested in here is we want to know what the hell this function is, right? So let's go ahead and we'll search this entire directory here for def get batch converter, and that should give us this. So okay, batch converter has two different truncation sequence length. So there's some truncation sequence, and then you have MSA batch converter and batch converter. So let's try the one that's simpler first to see what we get from here. So callable to convert an unprocessed labels plus string batch to a processed labels plus tensor. Okay, so it's basically converting this string into a tensor. So you're given some alphabet, and then that alphabet is used to encode the sequence string. So you take the raw batch, you split it up into the labels and then the sequence string. You truncate the strings. You get the max length for all the different strings that you have in there. Then you create an empty torch tensor of that batch size with the maximum size. This is the beginning of sequence token, and then this is the end of sequence token. So you're saying however long the longest sequence in this batch is plus the beginning and end of sequence token. So you're basically saying I have a batch of, I don't know, what is the length of this, for example? If we go here, let's do Python protein equals that. Protein equals, we're going to paste in that string. What is the length of this sequence? 65. So Control D, clear. So this is a 65 is the length of that first protein in the example. So when you append those, it'll be 67. Okay, so then you fill with the tokens. Okay, labels, strings, labels.append, strings.append. Okay, you're converting to int64 the encoded. you're encoding it using this alphabet. So I'm actually curious what the alphabet is. So if you go to our VS Code, I think there's, we go here, right? Maybe we come here. Can we debug? Okay. So, I mean, this is the kind of best use for VS Code, but we can go into ESM here, name, package, module spec, right? What we're interested in here is, let's take another step here. Step into, no, we want step over. ESM has no attribute pre-trained. It's because we need to pyenv activate ESM protein. Create a launch.json file, Python file. Tape program console VS Code use pyenv. Jesus Christ. Debug the current active Python file. Is there a way to select the environment setting? Close out of this. Yeah, this is what I want. ESM protein. Okay, that's the right interpreter. Okay, current file, configure, VS Code add pyenv configuration. Okay, that's what we have. We have the interpreter path. We have the right interpreter. Okay. Okay, so let's go ahead and put that in here. We'll put a comma in there. Property is not allowed. What if I move this here? Property is not allowed. God damn. Okay. Fucked VS Code here, guys. We're just gonna do it old school way. So let's go ahead and print alphabet. Maybe it does have a nice little string formatting that they made for us. So, okay, esm.data.alphabet object. Okay, so why don't we go ahead and maybe search the repo for this. So we're going to copy that. We're going to go and we're going to search for the alphabet object. esm.data.alphabet. So let's go ahead and look at what that class looks like. Okay, here we go. So this is a class called alphabet. It has a couple different properties here. It has the tokens, which is a sequence of strings, prepended tokens, append tokens, beginning of sequence, end of sequence, use MSA. Okay. When you initialize an alphabet, such as we did here, by pointing it to a pre-trained model, it creates one of these from architecture, MSA transformer, ESM1, ESM1B, invariant GVP. Okay, here are some of the tokens: class, pad, end of sequence, unknown, and mask. So this is the, whenever they train this, they use a masking task, so they kind of hide some of the parts of the some parts of the protein, and then they get the model to fill in the blanks. And that's kind of the unsupervised learning objective they use on this. Converts a string into a sequence of tokens using the tokenizer. Okay, and then this is the batch converter. Okay. So let's go back to our thing here. We have our alphabet. We have the batch converter. Associated with our alphabet, we put our model on the GPU. And now let's go ahead and give it some mini batch. Test batch. And we're going to go ahead and give it two different proteins here. So let's give it, this is interesting here. There's protein 2 and then protein 2 with a mask. So let's copy both of those and put them in here. And then move these up here. Protein 2 mask, we'll call it. And you can see that this is the same exact protein, except once we get to this part here, we're taking this H and we're masking it. So if you look at this, this is the rest of the protein. So the entire protein is here, except for the mask, everything except for this H. And I'd love to know how to go from protein to string. So how to go from protein to string for ESM. So maybe this is something like, if we go to Wikipedia, hemoglobin, right? Hemoglobin is a common protein. Is there subunit chromosome? Like, is there a long name for this? What if we type hemoglobin Python? This is not the right thing. Hemoglobin variance. No, that's not what we want. Okay, so we don't actually know what the hell this protein is, to be honest. First two sequences. Protein folding string Python how to convert DNA to protein in Python 3, visualizing and analyzing proteins in Python, a Towards Data Science article. Okay. Okay, PDB, Protein Data Bank. Okay. Okay, so PDB, Protein Data Bank format, Protein Data Bank format. The Protein Data Bank format is a standard format for containing atomic coordinates. Okay, so what does this actually look like? Okay, so there's like kind of an X, Y, Z position. This is not the same as this. This is a different type of format. Okay, so it's not Protein Data Bank format. What about CIF? MMCIF format. Crystallographic information. So crystallography is a way that you kind of determine the atomic structure of things, and this is probably the format that comes out of these machines. Okay, closely related is MMCIF, which is intended as an alternative to the PDB format. Okay, so there's basically, it seems like PDB format was kind of the standard, and then eventually it switched to MMCIF. Let's see if we can find an example of something in MMCIF format. MMCIF file. Format used for describing the structure of small molecules. Okay, we're going to go out of that. Okay, wait up. This is much more like we're looking. This is much more similar to what we're looking at here, right? This string here. This looks like this. This is the same kind of like all caps, letters all jammed together. So polypeptide. Residue sequence. Okay, so this is a residue sequence. Let's see if we can residue sequence lookup. Sequence search. Let's do it. Let's copy and then put that in there. This is totally it. K-A-L-T-A-R-Q-Q. K-A-L-T-A-R-Q-Q. So this is E. coli. E. coli residue sequences. We have the name of this protein. Can I copy this string? Can I copy this? Download file. What's in this file? Okay, here we have the, this is the DNA sequence. Structure, reference code, blah, 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 bunch of crap. Okay, where's the actual residue sequence here? This? Why don't we extract this to the same folder that we're in right now? Data, no, home, dev, betterer, bio. We'll put it in there. So let's save this. Let's open the CIF file. Let's see if we can find this in here, maybe just the first parts of it here. KALRQQ. Go in here, try to find that. Okay, so this is the full sequence. There's also an M at the beginning here. Let's see if we can find the whole thing in here. So if we take this whole sequence and Control F in here for the whole sequence. Okay, it is there. So why don't we actually take this entire sequence? Let's put it in there. Put the whole sequence in there. And actually we can get the length of this as well. (202). So the sequence in the example was 65, and it seems like the full sequence of this is 202. So let's see what happens if we put the full 202 sequence in there. And this is called a Lex A repressor protein. Okay. And this is Lex A repressor masked. And we'll take the same string as up here, but we're going to mask out. Let's mask out the T here. So it's MKAL, and then we'll say mask on the T. Okay, now let's go back to our opening here. And we'll create batch labels, batch strings, and then batch tokens, and then batch converter for test batch. Yep. Okay. Extract per residue representations on the CPU. So with torch nograd. So again, we're just kind of evaluating the model here. So we can just say, we can tell torch that you don't need to keep track of the gradient here. All right, so we have our results, model. Okay, so batch tokens. It's this part here. That's the tokenized with the alphabet that was used for this model. So converting it into a bunch of vectors that represent each vector here, rather than representing a token, which in a large language model will be kind of usually a word or a piece of a word. Here, the tokens represent residues, which are small little subparts of proteins. So we'll say batch tokens. You see here, GitHub Copilot actually wants me to put this on the GPU here, .CUDA, right? So let's actually do this on GPU. Batch tokens .CUDA. Representation layers is not 33 because I think this is the smaller model, right? This says T33 here in the example. We loaded the T6 model, so we actually want the 6 right there. And then return contacts equals true. Okay, so it's going to return that. Let's do token representations. And we want the 6 elements of the representation. So let's actually print that out. Print token representation shape. Python. Okay. So this is the batch size, right? And we just have a batch size of 2. Again, we saw that the longer protein structure here, or this longer residue sequence, is 202 residues. And we saw that the length adds the beginning of sequence and end of sequence token. So the total size of the kind of sequence length here is going to be 204. So even if you had a smaller one, you would be basically wasting a bunch of your tensor would be wasted because it's sized based on the longest sequence. So there's probably some stuff that they do when they're actually training where they basically try to get smaller sequences together, or they have padding. And then 320. I don't know what this 320 number is. I guess that's the size of the alphabet, maybe. If we go back to, there was a property on the alphabet, maybe we can look at it that gives us the length of the alphabet. Yeah, so you can look at, there's a dunder length method implemented for the alphabet object, and let's go ahead and actually call that and print it out so that we can see exactly how many. So let's do a little print here. Print f string, of course. Length of alphabet is, and then there you go. Look at GitHub Copilot telling you the right thing to do there. Let's go ahead and run this. 33. So that's not 320. So I don't know where this is coming from. where is this coming from? Let's go back. Okay, splitting, batch converter. Okay, here you go, the batch converter. Labels, strings, tokens. So this is where the 320 comes from. Torch.empty, it's the batch size, the max length, padding, index. Okay, so maybe it's adding some padding there. I think that might be what's going on here. So they have like, this model is designed to have a bunch of padding on it so that you can probably fit larger sequences. Okay. Generate per sequence representations via averaging. Note token 0 is always beginning of sequence token, so the first residue is token 1. Okay, so they're going let's see what they're doing here. See what they're doing. Sequence representations. GitHub Copilot wants you to do this. It's slicing here, so it's saying the 0th, right, the middle dimension we saw is the actual full sequence, so this is saying the 0th one, so I don't think that's correct. We just want to initialize an empty list here. Okay, so now we got our test batch. We're going, right, there's going to be labels, strings, and then tokens. So really this is the label here. This is the strings, and then this is the actual sequence. So we don't need this apparently. And let's go ahead and remove the start and the end tokens. Okay. So GitHub Copilot here automatically is saying that what you want to do here is remove 1 to length of sequence plus 1, right? So you're removing the beginning and the end, which is actually what's happening here in the example as well. They're removing the beginning and the end, and they're taking the mean at the 0th index. I wonder, I don't think this is actually very good because you're using Python to loop through this test batch, and then using the built-in Python mean. I think you'd be better off vectorizing this directly in PyTorch, because I bet you the mean operation in PyTorch, especially on a large batch, is going to be way faster than iterating through all of this in a for loop in Python. But I think this is just the example. Maybe they want to kind of show a little bit more clarity, easier to read. So, okay. Then they have that. And then the last part here is look at unsupervised self-attention contact prediction. So import matplotlib pyplot plt. Let's go ahead and actually put that at the top here. Again, formatter. We're gonna auto format our code here. There we go. Makes it look nice and pretty. Save that. here. For blank and sequence. And then attention contacts in zip test batch, that is correct. Results contacts, the first 6. I don't know if we need the first 6. You can probably get away with that. Attention contacts equals attention contacts 1 to length of sequence plus 1 and 1 to length of sequence plus 1. Okay, I don't think you need to do this because we already got rid of the first one, so you can just, or already got rid of the beginning and end, so you can do this. Figure size 10 by 10, show attention contacts dot CPU into NumPy. We'll call this the sequence and we'll do plt.show. So let's go ahead and run that. Okay, pip install matplotlib. You're gonna install matplotlib onto this environment here. All right, now we're going to, oh, we already did. Now we're gonna run this. And there we go. So this is the attention map, or the contact map, right? So attention contact. So right in this transformer architecture, every part of the sequence can pay attention to every other part of the sequence. And I think in this ESM model, that's like roughly, you can think of that as the likelihood of there being a contact between these two molecules. So we see here that, for example, a long part of the, like once you go past the 60th protein in this sequence, these barely contact each other, right? So intuitively what we should see is kind of like a bunch of contacts in the first part of the sequence, and then there's this kind of long tail that maybe is folded in half. So let's see if that prediction is true at all. So we're going to go into our Chrome, then we're going to go to this. No, we want this one. Okay, and that is kind of what we see, to be honest. If we look at the 3D structure for this 3D view, right? I don't exactly know where it begins. Maybe this first part here. Yeah, so it begins here, and we can see that there's some complicated stuff going on here with the folding, but then it kind of, maybe none of this kind of looks like it's still fold, so maybe even just a faint color here indicates folding, and there's one kind of like really strong. Oh, okay, actually this is more interesting. So yesterday we learned about homodimers and heterodimer proteins. So homodimer proteins are proteins that kind of like glue to themselves, right? And they're kind of like two halves, right? The top and the bottom half of a Pokeball kind of situation. And I think that's what we're seeing here, is that this orange part is the same molecule. They're just, the reason they're showing it to you in this 3D view is because it kind of like, it tends to glue with itself anyway. So really, I think only this green part is a single sequence. And you see how it kind of connects to itself there. Okay. So let's close out of that. Oh, and it's showing us the second one, which is the same. Okay. Let's go back to our Chrome here, back to the example. Look at the unsupervised self-attention map contact prediction. So another thing we can do here is we got the results here. So let's actually look at what's in the results here. Results includes string results. Here, look at this. GitHub Copilot is telling us to print out the keys. Okay, we're gonna go here. Length of alphabet is 33. We can close out of this, close out of that, and we can see the results here. So there's logits, representations, attentions, and contacts. So let's look at the token representations. Print token representations. Let's see what that looks like. Okay, so these are still in a PyTorch tensor, and they're not converted back to tokens. They are in tokens, they're not converted back to a residue sequence, which we can read. So is there an alphabet.untokenize operation here? Is that what a sequence representation does? Is that really what we're doing here? So I think this sequence representation here might be the torch.stack sequence representations. I don't think that's exactly what we want to do. I think we just want to print this, see what it looks like. Let's comment out the plt.show so we don't have to keep exiting out of that. Okay, so these are the token representations. These are much smaller, maybe not, right? E to the -2, e to the -1. There really isn't any big numbers here, so it's all just like these tiny numbers. You see, like, compare this to the just the representations up here, token representations. You have something like a 0.95, right? And then you have something like a -0.05. So there's much more of a uniform kind of spread over -1 to 1 versus here all of these are small. Okay. Going back to here. I'd love to be able to turn this back into, let me see if there's, in this alphabet, is there a untokenize in code? To dict, get toke. How do I convert these float vectors back into a sequence. Read fast A. Okay, so here, kind of the second part of this example here, they're showing you how to load the ESM fold model. So, and then they're gonna load it as a PDB file, right? The protein database file, not Python debugging. So import biotite.structure.io as BSIO. Okay. For some reason, I feel like that's not going to work. Let's actually test it out here. Python import. No module found biotite. Okay. Biotite PyPy. Biotite is your Swiss Army knife for bioinformatics. Whether you want to identify sequence regions in a protein family or blah, 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 Biotite is the right tool for you. Okay, cool. Let's install that. Pip install Biotite. How often are they releasing stuff for this? Wow, this is actually very good. Look at this. Every couple time, like basically every couple months, they release a new version. And this is, there's a lot of stuff here. This has been working on for a while, up until 2017. Let's actually go to the repository, see what that looks like. Biotite dev, Biotite. Not a ton of stars, but we can star that. Top contributor is Patrick Kunzmann from Germany. Let's go ahead and give that guy a follow. Molecular biotechnologist, Python and pun lover. I bet you this this means something. Let's see. DNA converter. DNA to mRNA protein converter. Let's see what we do when we get that in there. Output strand, input strand, protein. Okay, what if we copy this protein into our little example script here? So if you just joined, we are copy pasting the string on this random GitHub guy's info into a mRNA, and then from the mRNA we got the protein, and then we're going to put the protein here. So we're going to say random GitHub protein. We're going to put that in there and see if we get an error here. It doesn't look like it's quite the same, but let's not print out these shapes anymore. We can actually delete this and then say instead of printing out the whole, let's do token representation shape, and then say token representation dot shape. Okay, and we'll do the same thing but with the sequence representations here. Sequence representations shape. Okay. Let's rerun this. List object has no attribute shape. Gotta go back here. And we'll just say the first one. Okay. Token representation shape 160 320. All right, so this sequence is 60 long. It's a batch size of 1. We're only looking at 1 protein. And the sequence representation shape is 320. And actually, if we go and we show the attention contact maps we see there, there's the contact map. We have our 60 by 60, and it really only touches kind of in the middle here. Okay. Let's go back to here, Control W, Alt 3, and let's try to load our new protein here. So we're going to do a different model here. We're going to do model fold model. Let's call it fold model. Folding for structure prediction. Our fold model, we're going to say is ESM.pretrained ESM fold v1. Let's see if they have a smaller one because my GPU is small. Let's go here, Alt 4. Okay, so they have ESM fold v1 and then ESM fold v0, and both of these are absolutely massive. 690 million parameters. Jesus Christ. Okay. We can try to load this. I'm going to download this, see how long it actually takes. So let's go back to here. Do Python import torch, import ESM. Go ahead and put that in there. No module named OpenFold. Okay, we need to pip install ESM fold. After installing ESM fold, I think we didn't get the right thing here. Pip install, here we go, OpenFold. So these two dependencies here. And then this one. So DL logger and OpenFold. We can actually go to the GitHub the GitHub repo for OpenFold, see what that looks like. Damn, we were so close. It seems like OpenFold is uses a PyTorch that uses CUDA 11.7. We want CUDA 11.6 is what we have on this computer, so we'll see if this is a deal breaker. It might be a deal breaker. Yeah, it just didn't even install it. So let's go to the OpenFold Git. This one has more stars here. Trainable, memory efficient, and GPU friendly PyTorch reproduction of AlphaFold 2. Okay, so OpenFold is basically AlphaFold. Okay, if we look at the setup.py, where's the specific PyTorch version here? Get CUDA bare metal version. This actually seems like a clever setup.py. It looks like it's actually looking at the version that's on your computer. Maybe we could clone this. Let's git clone. We're going to actually download the OpenFold repo, go into OpenFold, and inside the ESM protein Python environment, we're going to pip install -e dot. Okay, build extensions, self-run command, install for development. What if we python setup.py install? What if we, let's search this. So let's close out of ESM. Let's open up a VS Code in here. And we are going to Control F this entire repo for CUDA. And we're going to see where it keeps trying to use CUDA 11.7. You know, that doesn't seem like it's anywhere. I don't know, guys, we might not be able to get the OpenFold here. Maybe we use an older version. Let's look at the releases here. Okay, there really is just one v0.1 here, v1.0. install PyTorch CUDA 11.7. Do they have the command here? CUDA 11.7 is backwards compatible. Anything CUDA 11.x should be fine. You know, that's not our experience though, because it seems like in our case, when we try to install, it doesn't like it. All caps. What if we do this, and then let's do torch 11.12 plus CUDA 11.7. We don't need torch vision or torch audio. Let's get rid of that. Let's see if there's a 1.2. No matching distribution found for 0.12 CUDA. Okay, it's actually 0.13.0 CUDA 1.7 or 11.7. Okay, there we go. 1.8 gigs of CUDA coming at you. All right, so once we get the right version of CUDA here, we can install OpenFold, and then we can go ahead and run this example here. So we'll wait for that. While that waits, let's go to here, back to this example, then we'll look at what's going on. So we have, we take our model, we're going to do ESMFold v1, and again, ESMFold v1 is apparently just the open sourced alpha fold called OpenFold. Okay, something happened here. Application Visual Studio died. Cool. Let's go back here. Okay, so this seemed to install. Let's see if we can install OpenFold. Still nothing. Import torch version torch.cuda is available, something like that. CUDA is available PyTorch. Torch.cuda is available. True. Torch.cuda. Is there a version? Get device name. Yeah, it's the right thing. Double long int init has magma, has half precision. Is there a cuDNN or something? CUDA status. Torch CUDA version. How to check print torch.version.cuda. Okay. torch.version.cuda 11.7. Okay, well, what the hell then? What the hell, OpenFold? Okay. Pip install dash dot. The detected CUDA version 11.6. That's not the version that's installed on this Python pip environment. If we go back to here, okay, I see. The problem is that we have CUDA 11.6 on our GPU. All we did was just install a PyTorch corresponding to CUDA 11.7, but CUDA 11.7 is not actually installed on this. Install CUDA 11.7. CUDA 11.8, we're already outdated. All right, we're not actually going to do that. Fuck all that noise. Why don't we go ahead and try to do what this notebook here was doing. Close out of that. And this notebook here was visualizing the CIF format, which we do have. We do have this 1JF CIF, which is the E. coli protein that we were looking at. So from bio.pdb, so let's do from bio.pdb import, and we're going to want to import mmcif parser. Okay. We might not have this dependency. Let's make sure. We do. Okay. So we do have that dependency. What about actually these other dependencies here? Import nglview as nv. No module named nglview. nglview pypy. IPython widget to interactively view molecular structures and trajectories. nglview, which is released from nglviewer. WebGL protein viewer. Okay, if only we could read Java, right? Let's go back here. Okay. Jupyter widget to interactively view molecular structures and trajectories. Utilizes the embeddable NGL viewer for rendering. Support the PDB protein database. Simple traj. What is this? Lightweight coordinate only trajectory reader based on code from Gromax. Okay, so this is like the trajectory of a protein. Yeah, I don't think this is going to work in normal Python though, because this is IPython or Jupyter. And then IPy widgets. IPy widgets are interactive browser controls for Jupyter notebooks. Okay. So why don't we actually make a viz.ipynb, make a notebook in here. Let's go to our VS Code. We'll open up the viz. Okay, so it's not, we made it in the wrong place here. We made it in OpenFold. We want to move viz.ipynb to dev betterer bio. That's where we were putting it. Okay, clear. Go back to here, try to open it again. Viz, there we go. Come back here. Let's import our little parser here. Let's also import nglview as nv, and we'll also import IPy widgets. Okay. We're going to have to install this. So pip install nglview and also IPy widgets. Okay, come back here. Oh, Visual Studio Code died. Super Objects has no attribute IPython display. What is this? Is VS Code being VS Code? Okay, so it looks like IPy widgets 8 is fucking broken, so let's go ahead and install this version here, 7.6.0. Okay, it installed like 400 other things. Let's go back to our VS Code. Definitely still having issues. Let's see what nglview, whether it actually installs an IPy widgets here. IPy. Install requires Jupyter Lab widgets, NumPy, and IPy widgets greater than 7. So let's install 7.0. Let's Jupyter Lab widgets, and I think we already have it with NumPy. Okay. Now let's go back. Maybe when you restart the kernel. Restart the kernel. There we go. All right. That's the right version of IPy widgets. Close Close out of that, close out of that, close out of that. Let's go to our visualizer. All right, and we're gonna do CIF parser. We're gonna create an instance of this MMCIF parser class. And we're going to get the structure of the molecule that we wanted. Let's go back to the Python, let's go back here to the protein database. This is actually 1JHF is the name of this protein. And the name of the CIF file is 1jhf.cif, I'm pretty sure. Let's see. 1jhf.cif. And this is the crystallography format. Okay. Let's go back here. Okay, so you get the structure, and then view equals nv.showBioPython. View equals nv.showBioPython structure. GitHub Copilot with the win there. Okay. Chain A is discontinuous at line whatever. Chain B is discontinuous at line whatever. Okay. Restart. Run all. This doesn't show us anything here. I wonder if it's because of VS Code. Maybe if we open it directly in here. So let's go to dev bio Jupyter. Let's do viz. Jupyter Notebook is okay. So we just open this with Jupyter. Let's run this. And we still don't get anything. Let's see if we download the PDB. And maybe the CIF again. So let's make a new terminal here. Ooh. Let's make a new terminal. Or actually, we can just go right here. Let's copy this PDB parser here. We'll put the PDB parser. Let's make this a little bit bigger so you guys can see. This is going to be 1JHF again, and in here we're going to do -home -trend -downloads ls-downloads -star-pdb. So 1jhf.pdb. 1jhf.pdb. PDB parser not found. We got to import it as well. PDB parser. Okay, we get the same warnings, and then it doesn't do anything. I wonder if maybe it's like saving it to some kind of We have both of the PDB and the CIF file in here. So go ahead. We don't need to have this download path anymore. PDB construction warning, chain B is discontinuous. Let's search Google for that. Going 3D, the PDB module. Okay, so it seems like you can give it capital permissive equals 1. Permissive flag indicates that a number of common problems associated with PDB files will be ignored. See if that helps. Okay, that didn't do shit. IPy widgets not showing. Okay, you need to enable the widgets. Okay, let's go back here, close out of that. Let's enable the widgets. Widgets are enabled. Let's rerun this. Re-import. Hasn't done anything. Okay, wait up. You need to, if you have Python environments, you need to use this to enable it. Okay, enabled it again. Let's run it again. Now let's run it again. Still nothing. What if we run this? Okay, just more commands to copy paste here. Okay, install, enable, let's run. Still nothing. What if I install this? Install pip install Jupyter Lab and Jupyter Server. Okay, so we have Jupyter Lab, Jupyter Server, bunch of shit, still not getting anything. So I don't know why we can't visualize this. NGL view not showing. Import ipywidgets, ipywidgets.txt, hello. Okay, so if that works, so I think you can do add code or like Control A or something like that to add a insert cell above and below. Okay, A. Okay, so we do have ipywidgets. Try to find any existing NGL Vue.js widgets folder and delete them and reinstall NGL Vue again. Okay, so remove -rf local share NGL Vue.js widgets. Runtime NB extensions. Okay. Library. No, this is Unreal Engine. About Jupyter. Jupyter Lab workspaces. No. NB config. Load extensions. So remove this. Okay. Okay, now we gotta no module named. Okay, so let's go, I think we had it open here, right? So we gotta close out of this. Let's install that. Install this. Okay, we're gonna close out of that, close out of that, close out of that, close out of that, close out of that. We enabled the widgets extension, widgets NB extension, and then we're also going to enable that. NGL view, no module, pip install NGL view. Okay, so NGL view uses a different version of versioneer. Let's look at NGL view. NGL view PyPy. Go ahead, go to the home page. Inside this setup, there'll be a versioneer probably. Okay. It's not what we want. We want to know what version of versioneer they're using. Versioneer 5.18. Okay. So pip install versioneer 5.18. Pip install NGL view. Cannot import name, get command class from versioneer. Maybe if we install a newer version. Okay, so we got installed 0.19, installing 0.28. Let's see if now we can install NGL view. Nope. Pip uninstall versioneer. Yes. pip install nglview. God damn, this is so annoying. nglview version year. Okay, here we go. You have to clone nglview. W, close out of this. Alt W. Close out of that. Control C out of that. Let's make a new terminal here. Clear. Let's go into dev. Let's pyenv activate ESM protein. Clear. Let's git clone. Don't need the git clone part. Git clone nglview. Let's go ahead and go into that folder, nglview. Let's python setup.py install no module named Jupyter packaging. Okay, pip install Jupyter packaging. Pip install dot. Okay, should install the dependencies. Installed nglview. Okay. Okay, then these are the lines that we ran beforehand, but we'll go ahead and run them again. It's enabling these two Jupyter extensions. Okay, now let's do Jupyter Notebook, and we'll try to open our viz.ipynb. So now we have it open. Imports work. The text works, but these parsers do not work. Let's close out of these. We'll give this guy a little emoji here. Rocket ship. If we're coming up with that. Okay. NGL view show biopython. NGL view show biopython not showing. NGL widget does not appear. Can you report view.ngl version? Can you try to activate NGL view? What the hell does that mean? Oh, you can say NGL view dash dash notebook name? Huh. What happens if we give it our notebook name? Thank you, more jelly. I'll give you a heart. Okay, so I think we're starting to get here. So let's import this biopython here. Okay, those imports do work. Let's go ahead and see what this does. Still nothing. Oh no. Okay, so NGL view is just a bunch of hot garbage. That's basically what I'm learning here. It's not just normal garbage, it's hot garbage. I don't think this is leading anywhere, so we will maybe come back to it. I can debug this in my own time just to not waste your guys' time here. Delete. Clear output of all cells. Don't save. Cancel. Overwrite. Okay. So what are some proteins? Most common proteins. Collagen. What happens if we search for collagen in here? Okay, so there's a couple different things here. NMR structure of heparin binding site of non-collagenous. Structure of the human collagen X NC1 trimer. Crystal structure of the collagen triple helix model. Cool. Why don't we import this into our little ESM tester here? Let's go up here. We'll say IK6F. Maybe we'll link to this protein data bank here. And see if we can copy the sequence here, the residue sequence. There has to be some fast way to copy the sequence on this website, right? I feel like that's kind of like the whole point. Because right now, the way I do this is I download the MMCIF, and then I open this CIF, and then inside here I copy actually, you know what? I bet you there's a way to get the Biotite MMCIF parser. Can I get the let's try to do this. Try to oh wow, that's quite crazy. So let's put in our MMCIF parser here. Here we're gonna try to load the 1K6F. This is gonna be 1K6F, 1K6F.cif. Let's go ahead and go into, actually we already have a notebook there. Let's copy what's in our downloads, this 1K6F.cif, copy it here, come back here, and view, whatever, screw the view, but structure, let's just print that, see what happens. Let's run it. Structure, can we like dot center of mass, child list, detach, get atoms, get chains, get iterator, get list, get parent, get residues? This is a generator, so maybe residues equals res for res in structures, get residues. Okay, can we print out residues here? Pro G HOH, so this is okay, like residue objects. Let's do bio Python get residue structure from CIF. MMCDIFO. Get structure, save structure. Accept chain, accept residue. Okay, residue. Get residue name is disordered. Sort add. Return the segment identifier. Maybe dot get seg ID. Okay, that does nothing. Get atom. Doesn't exist. Okay. Get res name. How about that? Glyc, gly, gly, HOH. Okay. Can we say biopython CIF parser to sequence string to residue sequence? We're still looking for this, right? Maybe we can look at the, let's look at the other CIF file that we had and then, right, let's copy paste this. Let's open up our 1JHF. PDB sequence 1-letter code. Okay, so it sounds like 1-letter code is maybe the right word we want to search here. BioPython 1-letter sequence, 1-letter residue sequence from MMCIF. Exact residue sequence from PDB file. Interesting. Okay, so here in this, accept all cookies, in this Stack Overflow, a couple of people give answers to here. So this guy's, he's basically saying, how do I get the residue sequence from a PDB file, which is basically what we want. And this person's saying, hey, well, actually, you can just use a dictionary and then convert them. So basically, rather than have the kind of like 3-letter stuff, you just convert it. But okay, so actually you can import Let's try this. Control P. Let's open our notebook. So from bio import sequence IO. Okay. We're gonna get rid of that. From bio.pdb import mmcif parser. Okay. We're trying to load the structure from a mmcif file. And we're specifically trying to load the residue sequence, the one-letter residue sequence from the mmcif file. So we get the structure, although here it seems there's these parsing sequence IO parsers here. So let's see, for record in sequence IO dot parse. Okay. Turn a sequence file into an iterator returning sequence records. Handle the file or a file name to the string. Format, lowercase string describing the file format. Alphabet, no longer used, should be none. Okay. So let's see if we do this. 1k6f.cif, and then maybe we say mmcif. And let's print the recorded sequence. Unknown format mmcif. Let's just try CIF then. Unknown format CIF. So bioseq.io. Maybe it's just structure dot is that it? Is GitHub Copilot giving us the correct answer here? No, this is not right. Pro GLY, pro GLY, pro GLY, and then just OH, 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 O. Doesn't seem like the ones that we had up here. These seem a little bit more complicated. What if we try to do this with this one? We'll see if it works with the PDB file, and then maybe we can convert this CIF file into a PDB file. Let's comment this out. Unknown format PDB. What formats are allowed? Clustal emboss, Masta, Math. These look terrible. None of these look like a PDB or a MMCIF or anything that looks familiar, so this was not good advice. Oh, okay, here we go. These are the ones that we want. We have PDB atom, CIF atom. Let's try CIF atom. Well, first of all, we can do PDB atom. Okay, that's definitely what we want. And now let's do CIF atom. And we'll print this one too. Okay, that looks like it too, right? PPG, PPG, PPG. I think that's what we want. Okay, so we can actually take these into our little structure here. So test batch. This is going to, we're going to move this down. This is our E. coli residue sequences. Then we're going to have our 1K6F, where test batch is equal to this. And this is going to be 1K6F, I don't know, say part I. Right? And then we're going to do a little list comprehension here for I in enumerate seek IO parse and then here you have res and then no, it's going to be a tuple, so a tuple here where the second part of the tuple is the res sequence. Okay. We're going to go back to our notebook. Oop. I don't know how we undo that. Okay, there we go. Back to our notebook. We're going to copy the sequence IO from this. Get that dependency in there. Okay, so we have that one. Now let's do the CIF. Okay. And why don't we actually, is this going to be 1J HF. And let's say plus equals, so we have all of them in there. Okay, so basically we added the PDB and the CIF sequences in there. Let's run that. Okay. Cool. We have some discontinuous chain warnings. Longest sequence we have there is 200. And we should actually print out some new lines just so it's clear, and then let's print out test batch. Okay. Yeah, so this is what I wanted to look at. So this is the same protein, right? Here, Lex A repressor as the one that we loaded from the PDB file. Right, it's the same as this one, the first part of this 1JF, right? What's interesting here is that KALTARQQEV, KALTARQQEV. So this M part there got removed, right? And actually that was also the case here. KALTARQQ, there's no M. So I wonder what the M means. I wonder if that's like some kind of empty token or something like that. Cool. Let's save this. Couldn't load ESM because of the CUDA situation. ESM fold inference. Compute embeddings in bulk from FastA. We provide a script that efficiently extracts embeddings in bulk from a FastA file. What is a FastA file? Bioinformatics, the FastA is a text-based format for representing either nucleotide sequences or amino acid protein sequences. We've discovered it. E. coli residue sequences, FastA. So is single letter residue sequence strings the same thing as FastA? Okay, so here we have, okay, what is the M? So the M means bases with amino groups. Okay, so I suppose you can remove the M and you don't need to have that M. Amino acid start codon. Oh shit. Okay, so that's what the M is. So the M this is crazy, man. Like GitHub Copilot knows about biology. The M in the FASTA file is the start codon, comma. So it's not a residue? I think it is, right? The start codon always codes for methionine in eukaryotes. It seems that this is not this is not the same format. So the random GitHub protein that we found is not in that format, or in the FASTA format. Alternate start codons are very rare in eukaryotic genomes. However, naturally occurring non-AUG start codons have been recorded for some cellular mRNAs. Mitochondrial genomes use alternate start codons more significantly. AUA and AUG. Yeah, so everybody knows mitochondria, the powerhouse of the cell, right? They have their own separate genome. And it seems like they actually have different start codons as well. A CUDA device is optional and will be auto-detected. Okay. Directory, CPU offloading. The output values are average log likelihoods over all amino acids in a sequence. Cool. I'm starting to run out of steam here, so I think what I'm going to do is I'm going to push this, and then I'm going to go eat, and I'll return with some more stuff here. But let's go ahead and add all of these bad boys. And we'll do folding with ESM. Commit. Sync. Alright guys, thanks for tuning in. This was looking at ESM with Hugging Face, although we never actually ended up using Hugging Face at all. But yeah, I think we'll try to do that maybe tomorrow, see what happens from that. But